Hey guys, welcome to my YouTube channel. In this video, I am going to be discussing the double spending problem. We are going to be looking at different scenarios that can happen and how Bitcoin tries to prevent the double spending problem in the blockchain architecture. So let's start by discussing what is double spending. What is the double spending problem? So if you have a currency, let's say I have a dollar currency and I am able to spend the same currency to two different people. That means I am using the same $1 bill. In a very fundamental sense, I'm using the same $1 bill and I'm buying maybe some chocolate and buying some other commodity using the same bill. Then I would say that if I am able to do this, then I would say that this type of transaction have a double spending problem. So let's see how and in which transactions it can occur. So there are two types of transactions. First one is physical transaction. The second one is digital transaction. So let's see in physical transaction, can double spending happen or not? So in physical transactions, if we are able to duplicate a physical unit of currency, then we can say that I am able to generate a new currency. Let's say if I have a dollar bill and somehow I crack the way it is developed by the government or the central bank or anything, the authority that is in existence to generate the currency. So let's say if I am able to copy this bill. So this is the real one and this is the duplicate. Let's say if I am able to do these things, then I have a double spend problem. But if you see, practically there are various factors which will stop me from doing this, going from real to duplicating my currency. So what are these factors? These are the factors like paper used in making the currency, holograms, and various other identities issued by the government or the authority which generates the real currency. So practically making these all, developing the currency, keeping in mind all these factors accurately is very hard. So it is practically impossible. So in this way, in physical transactions, we are not able to duplicate the same currency bill. And of course, if we try to, let's see the other scenario, if I have a $1 bill, or let's say I have a coin, then of course, naturally, obviously, it is not possible to give the same coin to, let's say, some shopkeeper and use the same coin for your parking fee. This is obviously not possible. So we can say that in physical transactions, double spending is not possible. Now let's look at the digital transactions. So in digital transactions, we are talking about two types of transactions. One is the online banking transaction. Another one is the cryptocurrency based transaction. Let's call this A and B. So the A transaction, which is the legacy banking digital transaction, which we traditionally use to transfer money from one bank account to another. Legacy banking transactions. So let's see what happens in these legacy banking transactions. So let's say you are a user A, you have a bank account and you initiate a transaction T. So this transaction first goes through a mediator, which we call a central authority, and this authority is responsible for verifying validating your transaction. Only if this is done and your transaction is found to be genuine, it will process that transaction, and then it will reach the bank of your merchant, and finally eventually it will reach the merchant. So legacy banking transactions are governed by the central authorities. So these central authorities, there can be many central authorities. So they each of them maintain a private ledger. Let's say if they have something like from table, from where whose transaction it is and the transaction amount, and then to where it is going, etc. Something like that. It's just an example. So each of them will have a private ledger like this. Now the problem is, why are we trusting this central agency? Let's say the user A and the central authority had some deal. Let's say they had some deal and they both tried to make a double spend. To avoid this, the government agencies or the central authorities or the central bank of the country will keep a regular, frequent check on the central authorities. They will maybe check their private ledger, or they will check for any malicious activity. And if found guilty, there are stringent laws and can even lead to lifetime ban. So as a result, due to these stringent laws and lifetime ban, the central authorities generally do not indulge in any malicious activities. So consumers can trust them easily. But there are some issues with central authorities, like there are some disadvantages. Let's see what are the disadvantages. So before moving to disadvantages, due to the stringent laws and actions that government will take, as government is keeping an eye on them, there is generally no case of double spend. And if there is any case, the government will take strict action, and the other central authorities, there are multiple, right? So the other central authorities will eventually do their work honestly. So in this case also, the double spend problem is minimized. It is almost impossible to do. Like practically no one will try to shut down their own business. But what do these central authorities get if they are doing verifying? If they're verifying and validating our transaction, they must be getting something in return, right? So they have fees. If you have seen, they charge some fees for transactions. So these are the disadvantages of central authorities. To pay something to someone, we have to pay for someone else to verify that we are paying to the correct person and paying what we are promising, and we actually do have what we are paying. So to just to verify and validate that, we have to pay someone else to do that from our end. And also they have restrictions such as minimum transaction amount. They have restrictions on methods of transactions. Sorry, methods of transactions. Methods of transactions and the time taken for verification and validation. So these are the disadvantages. They charge high fees and they have a minimum transaction amount. Like I can't send zero point 0.5 of a dollar. They have minimum transaction amounts, and they will have different types of transactions. And the time taken for verification and validation will depend based on those different types of transactions. So due to this, consumer will face many sorts of problems. As a result, we try to develop a system which is decentralized. This we call blockchain based transactions. So this is our B part. Online banking transaction has central authorities, and cryptocurrency based transaction are decentralized. So let's see what happens in that. Decentralized blockchain based transactions. Just a quick note here. I'm not going to go into deep into blockchain. However, I'm going to be giving a brief introduction and straight away diving into different scenarios as to how double spending is prevented in such a decentralized system. So let's first understand briefly what is blockchain. So there are no central authorities and transactions take place directly between peer to peer. So in case of central authorities, we had a private ledger. In blockchain, we have a publicly distributed ledger. Publicly distributed ledger that can be accessed by any node in the network. And the part of trust. How will I trust that my transaction? How will anyone trust that your transaction is genuine? So to gain trust or allow only honest transactions, blockchain or more specifically in this case Bitcoin uses a mechanism called proof of work, which is basically a computationally heavy mathematical problem solving task which is performed by nodes, task done by nodes which are called miners to confirm batch of transactions. So there are some nodes called miners which do a computationally heavy task and confirm a batch of transactions. That is, they validate the batch of transactions. Again, as said before, I'm not going too deep how they validate, what exactly they do. You can dive into that later. But basically, miners solve a hard but computationally feasible mathematical problem, and then only can they add a new block or new entries to the ledger. So a block is nothing but a timestamped batch of transactions. Now let's try to look at different scenarios which can happen in the Bitcoin blockchain and how exactly the double spending problem is prevented in Bitcoin. So let's say we have three people. We have Alice, we have Bob, and we have John. So these are the three people between which we will see transactions. Let's say Alice has an UTXO which is worth 1 Bitcoin. So in Bitcoin world, we don't store the Bitcoins directly. We see them as an UTXO. UTXO is nothing but an unspent transaction output. So let's say Alice has an UTXO which is worth 1 Bitcoin, and Alice tries to send 1 Bitcoin to Bob, and simultaneously tries to send 1 Bitcoin to John as well. Let's say he intentionally or unintentionally she tries to send. Now let's call this first transaction Alice to Bob as T1 or A1, and this one Alice to John as T2 or A2. Now in Bitcoin, whenever a person or a node initiates a transaction, it is broadcasted to all nodes in the chain network, and these nodes store the transaction into a pool of transactions called Mempool. So now since Alice initiated a transaction T1 or A1 of transferring 1 Bitcoin to Bob, it will be broadcasted into the network, and every node will store this transaction in an unconfirmed state. That is, they have not processed that transaction, not confirmed it yet. So all the unconfirmed transactions are stored in the mempool, which is a pool of transactions. So now this A1 will be stored in the pool of transactions, and A2 will be also similarly broadcasted to the network nodes and will be stored in the pool of unconfirmed transactions. Now let's say if both the transactions get confirmed and are mined into a new block. Just just imagine if both the transactions are confirmed and mined into a new block, then we have a double spend problem here. Because Alice only had one Bitcoin, but it transferred one Bitcoin to Bob, as well as another transaction transferred one Bitcoin to John. So one more Bitcoin was generated. So if this happens, then it will be a double spending problem. Now let's try to see the different scenarios that can happen. So let's write down scenario 1. Scenario 1, A1 is picked up into a potential block and A2 is still in mempool. Let's draw a mempool here. We have A1, A2 and some other transactions like A13, A15, many transactions. So let's say miner picks up a bunch of transactions. It picks up a bunch of transactions T1, T2, T3. I'm just referring T as a picked up transaction for a initiated transaction A. So let's say a miner picks up this transaction and he has A1 in it, in the bunch of transaction. And let's say that miner mines this block successfully. Then what will happen? If a block is mined, then it will be broadcasted to all other nodes. Now these nodes can accept or reject the block on the basis of the block's validity of transactions. So now let's assume that this was accepted. Now let's draw our chain status. So this is our chain. And this is the newly mined block. So this was accepted and it was mined and it contains our transaction A1. So A1 is now confirmed and processed. So what this means is Alice transferred one Bitcoin to Bob. This A1 is success now. Now meanwhile in the mempool, we still have A2 and other some transactions which were not picked up pending. Now let's say at some instance after this, A2 was picked up by another miner. He picked up A2, some other transactions T4, T10, something like this. Now if he mines this block successfully, and then when it is broadcasted, nodes will reject this one. Why? Because nodes check the validity of transactions, right? So basically in a pure fundamental way, node will see that Alice had one Bitcoin, but it is now transferred to Bob. Since the blocks are a publicly distributed ledger, they can see this transaction. They have this transaction in their public ledger. Alice transferred one Bitcoin to Bob. Now they are seeing Alice balance as zero Bitcoins. So Alice has no unspent transaction output. But the transaction that they received is Alice sending one Bitcoin to John. So that will be rejected since Alice has no balance left. So in this scenario, if you see one of the transaction, that is A1, is picked up and the block is confirmed and all other nodes validate that block, and then after that if another transaction is picked up, then there is no double spending problem. It has been avoided since one transaction strictly was picked up and confirmed before the other one. This scenario was an easy one, right? One of the transaction, that is A1, was picked up from the mempool by a miner along with some bunch of other transactions and was mined into a block and broadcasted into the network, and the network nodes also confirmed and validated that block and hence was added into the blockchain. And after this, another miner picked up A2 along with some other transactions, and it was mined into another block, and when broadcasted, the nodes which were validating or confirming saw that Alice doesn't have any balance now, so it cannot transfer 1 Bitcoin to John. Hence, it was rejected. And again, that transaction went into the mempool. Now, let's look at a complicated scenario than the previous one. Let's write it down. Scenario 2, A1 is picked up into a candidate block by miner M1 and simultaneously. So focus on this simultaneously. A2 is also picked up into another candidate block by miner M2. So in the first scenario, the first transaction A1 was picked up in a candidate block and later A2 was picked up, and hence it was rejected since the public ledger showed that Alice had used up all the balance. But in this scenario, we are talking about what will happen when A1 and A2 both are simultaneously picked. At the same time, both are picked. This can happen, right? Because there are multiple miners, there are multiple nodes. So a miner can pick up A1 from mempool, another miner can pick up A2 from mempool, both at the same time. So let's say the miner M1 created a block F1 to be added to the end of the chain, which contains A1, right? Since both of them picked up at the same time, let's assume both of them made a block at the same time as well. So now we have two blocks, F1 which has transaction A1, F2 also has transaction A2. But these two blocks can be broadcasted and confirmed, but they cannot be directly added to the chain since these both blocks are confirmed at the same time. So this will remain as a fork. So basically what I mean, this will remain as a fork of the chain. So this will form a new chain. Let's call it the candidate chain F1 and F2. Now different miners will start picking up other blocks and try to append to these fork chains, since they know that one of these chains will be confirmed and will be attached to the original chain, right? So other miners will start confirming other transactions into a block and add it to the end of these chains. So let's say someone will make an F11 block, another miner let's say made F21 block. So now I am again talking about both the fork chains are also growing at the same pace at the same time. So F1, F2 popped up at exactly the same instance. F11 and F21 also popped up at the exactly same instance. So let's say this is going on. The blocks are getting confirmed, but we are not yet sure which fork to be should we add to the original chain. But we know that the rule is that the longest fork chain will be added to the original chain, since we want the overall blockchain to be the longest chain. So this will go on. Let's say another F12 was made and F22 was made. Both popped up at the same time. This will keep on going. Generally, this will happen up to 6 confirmations. So up to 6 confirmations, they will have this fork chain competition going on. Both blocks popping up at the same time. Now, generally, if we wait till six confirmations, we will eventually get the longest chain. Let's say after six confirmations, either of F1 or F2, F1 or F2 will grow into the longer chain. At some point, one will be longer than the other, and the chain which lost will be again dissolved into the mempool. Its transactions will be dissolved into the mempool. Let's say F1 became longer. So let's draw the blockchain. Let's say the chain starting with the head as F1, which contains our transaction A1, became longer. So now if it became longer, then this chain will be joined with our original chain, right? Now since F1 became longer, the chain starting with F2 will be dropped into the mempool. The blocks mined but not added to the longest main chain go into mempool. By blocks, I mean the transactions. These blocks are called orphan blocks or stale blocks. So we saw that F1 was joined in the original chain. So as a result, A1 is success now. But since A2 was in the fork chain of block starting with F2, A2 is in mempool again. Mempool again. So as a result, this gives rise to the same situation we saw in scenario 1. So even though it seemed like all the blocks are being popped up at the same pace, exactly at the same time, and it gives the impression that A1, A2 may be executed at the same time, but we have to wait till one of the fork chain becomes the longest chain. So generally we wait till six confirmations. By the time we have six confirmations, we are sure that which chain will be joined to the longer chain. So eventually, even though it gives an impression of simultaneous behavior, eventually it is happening in a timestamp basis only. So after six confirmations, F1 or F2, either of these will be joined to the original chain, and the other fork chain will extract its transactions again into the mempool. Now again the same scenario like scenario 1. If A2 is picked up from the mempool again into another candidate block, and then the block is broadcasted to the nodes of the network, it will be rejected since the public ledger now contains transaction A1 and it shows that Alice has zero balance. Thus, the double spend will be prevented even though both are picked and candidates chains grow at the same pace. Eventually, only one chain will be confirmed and broadcasted. So, hence it is useful to wait till six confirmations and not just think that our block will be confirmed and validated within one confirmation. So if we wait for more six or more than six confirmations, we are very sure of which fork has been considered as the longest chain and joined with the original chain. Now let's discuss the third scenario. So scenario 3, what happens if a bad actor tries to change an already confirmed transaction or mimic it to some other transaction? So what will happen if someone tries to change an already confirmed transaction or mimic it to some other transaction? So this is basically analogous to the physical transaction case that we saw. What if someone tries to create a duplicate currency note, currency bill? What if someone tries to do that in case of a blockchain? So let's say we have a blockchain here. We have block. So these are all the confirmed blocks, and it goes on to the some block. So let's say there is a block number block 982. Let's say a bad actor tries to change this block. Since this is in the blockchain, it is already confirmed and verified, and all the nodes have it in their chain, and the public ledger on this block is also confirmed and verified. So now let's look briefly about a block structure. So a block will have a previous hash, its own hash, and list of transactions. So for now I am writing this, but there will be some more fields like nonce, gas limit, etc. depending on different blockchains. But for the case of this scenario, I just need to know these three things, right? So if block 982's hash changes, so if a bad actor changes something here, right? So if he changes here, changes something here, the hash of this block will change. Hash will change since the hash depends upon all the data in that block. But what will happen if 982's hash changes? 983's hash will also change since it points to a since it has the previous hash field which points to the hash of 982. And whenever any data changes, like whenever like if 982 blocks data changes, then it will again go into unconfirmed state, and it will be again be required to mine. But it's okay to mine a single block. Like if someone mines the block 982, if someone blocks 982 block, it's okay, it's just a single block, right? But since its hash changed, the other blocks will not find their hash, not find its original hash which was pointing which they were pointing to. So we will also have to mine the next block, mine 983, since previous hash field no longer exists. So in this way, if 982 changes, we have to mine it, but 983 will also change because previous hash changed. And since 983 changed, 984's previous hash will also change, and similarly 985's previous hash will also change, and it will go on until the last block. Let's say 993 was the end block of this chain, current end block. Its hash will also change. So if you can see, if a confirmed block is chained, all other blocks from that block to the end of the chain will have to be mined to reconfirm that chain. So if any bad actor tries to change a block, a confirm block, it will be in midst of the chain somewhere, and if it changes that block, its hash will change, and the next block that was pointing to some hash, previous hash, that will no longer exist. So we will have to change that next block's previous hash to this block's hash, and similarly it will have a cascading effect on all the other blocks till the last block of the chain. So now you can see this makes hard for the bad actor to mimic a transaction or reverse a confirmed transaction, because reversing or mimicking a transaction essentially means that he has to mine all the blocks from that block to the end of the chain. Now you can see this is the reason why we have the longest chain rule. Like you saw in the scenario 2, out of the forks which were popping out at the exact same time, we were waiting till until one of the forks get longest and we add that longest fork to the existing chain. So this is the reason why we need to have a longest chain, so that if any bad actor tries to change a block, he will have to mine many blocks. So we are trying to give him as many blocks as possible to mine if he tries to change any block. That is essentially if he's trying to change any transaction or mimic any transaction. So if we see in this scenario, theoretically it seems possible to publish a malicious change, right? If somehow, let's say the bad actor mines all the blocks quickly. Keep in mind that while he changes one block and mines all the blocks to the end of the chain, he also have to do it fast because there are other forks which are being built up, and if they at some instance overgrow his chain, then they will be added to the uh, original chain, right? So theoretically, even if it seems possible, even if it seems theoretically possible, practically it's impossible. Why? There are many factors. Let's write down the factors that arise if one tries to do it anyway. Let's say if someone is determined to change a transaction and mine all the blocks before any of the forks get superior lengthwise and get added to the original chain, he will face many factors. Computational power, he will need a hell lot of a computational power, or as they say, hash power. He will need lot of electricity or energy resource, anything, hell lot of an infrastructure. So if we try to analyze this and make out a cost, it will be very expensive for anyone, or even an organization, or even a continent or a country, to plan such an attack. It will be practically impossible to do it. So in this way, theoretically be it possible, but practically blockchain with the help of cryptography tries to prevent the double spending attack. Also there is an attack called 51% attack, when malicious nodes control 51% of the network node. So if this is the network, they control 51% of the network nodes and quickly mine and create their longest blockchain. So the goal of them is to control 51% of nodes, and miners quickly mine blocks and get confirmed fast and try to make longest chain fast. Since 51% of the nodes are their own, they will mine the blocks fast and they will get it confirmed fast, because 51% of voting they have in their own team, right? And they will try to make the longest chain. But why is it an attack? What will be they doing exactly? So let's say there is a block. In this block, let's say someone from the 51% nodes made a transaction of let's say they spent some 2000 Bitcoin. So now from the previous block, this block, let's say this is block 110. So this block 109. So this block contains the transaction of spending 2000 Bitcoin. So this was spent from a bad actor's node, right? So they will go back to this block 109, they will change it, or they will try to create a fork from here. They will create another fork chain from here. And since they have 51% of the nodes, they will try to create a longer chain as fast as possible than this honest chain. So B110, B111, B112 will be the honest chain. They will try to create a fork. FB110, FB111, FB112. So this fork they will try to create as long as possible faster than this honest chain. Why? What will happen? Because this chain will not have this transaction in it. So in short, they will spend 2000 Bitcoin for buying something or some commodity, but they will also reverse that transaction in this falsely created chain. But only if they own 51% of the network nodes. But even if they own the 50% of the network nodes, again the factors arise. They will have to keep syncing with their node partners. They will need a lot of computational power. They will be needing a lot of electricity, infrastructure. Many factors arise, right? So even 51% attack is minimized. I'm not saying that it is not possible, but it is minimized to a greater extent. So you can see in this way, even if sometimes theoretically it seems possible to double spend a Bitcoin in the blockchain, but practically if you try to do it, it is not possible for any single person or even a group or organization of people. So they will have to think something else. They will have to think smart or maybe create and find some loopholes in the blockchain. So yeah, this is how double spending problem is avoided or prevented in Bitcoin blockchain. So basically for other blockchains also the general idea will remain the same. Only the computational part, they will have different sort of techniques for that proof of work. Also there can be more stringent rules for other blockchains, but for the sake of Bitcoin, yes, this is how they try to prevent it. Thank you for watching my video. If you have any questions or if you have some more info on this, please do comment, like, share and subscribe. Thanks for watching. Bye.